How extreme can electromagnetic forces get on the surface of a neutron star or near a magnetar, where even the vacuum itself gets stretched to the point of sparking? In energy filament theory, this phenomenon isn't the result of magic, but a natural consequence of the tension and textures being twisted to the point of almost breaking. The energy sea itself is pulled into a high-pressure texture zone, where the high-frequency tension fluctuations, which once only caused slight undulations in the background noise of the sea, are now pushed past a threshold. This threshold forces them to form real filaments, and in the process, we witness the creation of actual electron and positron filaments as well as high-energy light filaments. To better understand this, let's compare it to a typical electric field around household electrical appliances. The electromagnetic field creates a relatively mild texture gradient in the energy sea, causing charged particles to move along this gentle slope. The disturbance is slight, with only a minimal tension difference, and although it may occasionally result in small sparks, it's nothing compared to what happens in extreme environments like neutron stars. Now, the surface of a neutron star or a magnetar operates on an entirely different scale. Here, the magnetic fields are so intense they can be billions of times stronger than anything found in a laboratory. This immense force effectively pulls the texture of the energy sea into very narrow, highly concentrated channels. And once particles enter these channels, they are forced to move at incredibly high speeds along these specific circulation patterns. Any attempt to maintain their original trajectories is immediately corrected by the intense magnetic forces. This excess tension in the energy sea is released through high-energy radiation, which manifests as light filaments and particle filaments being created and emitted. In such extreme environments, even the vacuum itself cannot remain passive. Normally, the energy sea is filled with high-frequency fluctuations, but these fluctuations remain at a level where they don't need to form into real filaments. The sea itself appears to remain calm and smooth on a large scale. But when extreme electromagnetic fields are present, these high-frequency fluctuations are suddenly confined to a narrow, textured groove. This intense compression of tension forces the sea to release the excess energy. The most cost-effective way for the energy sea to do this is by filamenting a few real circulating patterns. These patterns, which include particle filaments and twisted light filaments, are the result of the sea's attempt to relieve the excessive tension. And this process is what we observe as the vacuum being sparking or radiating. Magnetars offers the clearest demonstration of this concept. These incredibly dense objects have such a powerful magnetic moment that they carve deeply into the surrounding energy sea, creating tightly wounded, spiral textures. In such an environment, light traveling through the energy sea must navigate these spirals. And if its polarization or path is even slightly misaligned with the texture, the light experiences what we can describe as a tension penalty. The light is forced into the most energy-efficient circulation patterns, and this leads to observable phenomena like polarization dependence and birefringence. In simpler terms, the energy sea, when stretched to its extremes, only allows light to follow those circulation modes that require the least energy, and those that don't match are essentially blocked or redirected. This is why, in the language of energy filament theory, we say that the tension and texture of the sea are pushed to such extremes that only the most efficient modes of circulation can pass through. Thus, extreme electromagnetic forces aren't some newly discovered force that has mysteriously appeared. Rather, they are the natural response of the energy sea when its tension textures are stretched to their absolute limit. In these extreme fields, the energy sea essentially forces filamentation, produces high-energy radiation, and even causes the vacuum itself to spark as it tries to release the build-up tension. What we're seeing, in essence, is the energy sea's natural response to being pulled and stretched beyond its normal state of equilibrium. Tap follow, share it on New Physics, Clear Universe.